We have a chip that is used to glue chiplets in the Z direction, hence the name zGlue. And we have been working on this technology for about 3.5 years. We're out of Stanford University's Startup Accelerator, StartX. And we have a lot of scars that we accumulated over a period of time trying to develop this technology. And a lot of questions that I heard, we have somewhat come across them and tried to address them. But the thing is that we are a startup company. We have to figure out how to ship product. And we had a lot of pressure to actually launch something. And we did at CES launch a shuttle service where you can actually build a design using chiplets and get that in your hand in about a month's time frame. So Jim and Bapi asked me to talk in this forum, and they gave me some homework, which is to share my perspective on the proof of concept. But before I do that, I'd like to introduce my company a little bit. I'm not trying to do marketing, but really just trying to give you a perspective of what kind of things that we have kind of worked on. We are very happy to share some of this learning with the industry. And there's one glimmer of hope here that if a 3-person startup out of a Palo Alto garage can do it, then the industry can do it for sure, right? So in my mind, the biggest learning that I have is it's a business problem. It's a problem of market creation. Fundamentally, we are all smart people. We understand picojoules per bit. We understand maximum likelihood sequence estimators and all of that. But the issue that we have at hand is that we have this freight train with huge inertia coming with single chip that we have to kind of like put on a different track without derailing it, right? So my talk will essentially be focused on the assembly and test piece of it. And then I'll talk a little bit about call to action, and then we can discuss. Feel free to ask me questions. I will share whatever I know. Let me see if this video works, if that would help. So our idea was that we are going to use chiplets as a Lego block and give people Legos and tell them, hey, put these Legos together and you can build something. So we have this zGlue integration platform, which is an online tool. You can log in, make an account, and you can build zip chips. They are not exactly SIPs. They are built on the zGlue smart silicon interposer by using chiplets that are coming from third parties. So in this interposer, we have actually additional bill of material built into it. So in a typical flow, a developer essentially kind of goes in there, picks different chiplets coming from different companies, and in a traditional design methodology, make a schematic or write an RTL, then do a placement program. And what happens is the zGlue chip is actually kind of like an FPGA. It's not really a gate array. It's more like a connectivity array. So all the schematic that you do gets downloaded onto the smart fabric, and that essentially turns into an assembly and programming task. And then behind the scene, we're actually using pretty standard flow and pretty standard supply chain. We're essentially kind of managing them. And we have some products in the market that people have used already. And about 2 weeks ago at CES, we announced our next generation thing. So, when we started, the very first question was, where are you going to find these chiplets, right? And how do you put these chiplets together? No two companies will be willing to kind of agree on the same footprint. Going one level above, where there are architectural discussion like this one here is very difficult to have. And I'm so happy that, instead of going bottoms up, that industry is finally trying to go tops down, because I think that is the right approach. We have too many different options available on the packaging side, and on the hardware side. So for us, the issue was chiplet availability and the interoperability. We developed IP to make that a no-op. So one of the things that we have is we can take chiplets from anybody as long as you give us a piece of silicon with solder balls underneath and flip chip CSP or wafer level CSP, we can deal with that. The other big problem is business issues, right? Business issues like, whenever you talk to someone, you have to sign an NDA, right? And then just like, what is the die size? What is the I/O configuration? What kind of voltages do you need? It's just so much bureaucracy in this one that people are just not even willing to share very basic information. So all what we need to do is create a DigiKey-like thing. DigiKey where you go and buy chips. You just need something like DigiKey where you just go and buy chiplets. That's pretty much it. And leave the rest to the designers who put these things together, integrators who put these things together, they'll figure out the rest of the thing. They might use zGlue, they might use somebody else's fabric, but I think that is something that would be that would help quite a bit. The other thing is, if you think about these chiplets, design collaterals that you need to develop these systems, you need a little bit more information than you provide in regular chips. For example, let's say you want to do this proof of concept. You want to be able to simulate this thing in the beginning and make sure that interfaces are kind of operating correctly. In the end, when you produce some, you want to be able to test and find the yield and actually point fingers to whose chiplet is having yield issues. In order to do that, you need timing models. For example, you need RTL. But truth is nobody's going to share these things, right? So we have to think about what is the simplistic way that companies can produce something to enable these designers so they can take chiplet from this guy, chiplet from that guy, and they can design the silicon interposer or the organic interposer, whatever they are an expert in. Those kind of collaterals are just not available today, right? So we have to come up with a standard or an agreement saying, okay, if we want to create this marketplace for chiplets, let's start putting these collaterals out there with them and create an open market. The other thing is that the design tools coming from big three companies, they are just very much focused on single chip or they're focused on PCB. Very recently, they've started trying to put them together in the SiP market, but they are a struggle to work with. In 3D chip stacking, the biggest problem is thermal management, especially when you go in the high-performance systems of the type that we are talking about, and you need finite element models and be able to use multi-physics tools, which will be coming from not the top three, but some other vendors, or you will be going to the assemblers and doing that there. But there are a number of problems around the design tools which can be solved by exchanging information. So I believe exchange of information is something that needs to be solved. The other thing that we learned is testability is a complicated thing. So how do you debug a chip on a chip after it has been produced? Now what you need to think about testability and testing methodologies, how you're going to deal with that. There's a lot of IP from other companies that are already selling silicon on silicon type of solutions. They have developed some of those, but those are proprietary. It would be super useful to come up with something that industry can use and can interoperate. So this is a bit of what we had learned, and I'll now switch gears and talk about the POC. But I'm going to talk a little bit differently than just the POC one. So on this diagram, you see three options. The very first one is what we have been talking about, which is put silicon on organic, right, and flip that. So this particular solution is, as rightly pointed out, mostly available. And companies like Sun Microsystem used to ship products like that a while ago. So what's new in here? And I'll mention why I think this is probably the right step to start with. But you really want to go in the direction to your farthest right. But there's an intermediate step in here, which is, okay, go from organics to silicon. Biggest benefit, line space, and the type of bandwidth you can get with this many wire type of interfaces gives you tremendous benefit in terms of latencies, performance, and power. That's well understood. But there is a problem that happens in here. It's just an additional piece of silicon that comes in. That's the interposer. Somebody has to design it, right? And per square millimeter cost that you pay gets added on top. But the third one is where kind of the future is. So let me just dig a little bit deeper into each of these options. So if we go with this POC one, we have really kind of like, very well established back-end technology. We are thinking new things about the architecture so things can talk to each other. But the most important thing here is the business model, and the next equation, if you look at, will probably give you an idea. So when traditionally we're trained to look at these rectangles, and we look at their area, and we have some number in mind, and we calculate, okay, this is my bottom line to produce this thing. If I'm working at Sun Microsystem, all the pieces of silicon are mine, and the substrate is mine. I can very quickly calculate that cost and make a product where my margin will start making sense, and I'll be able to control costs. If you are getting these chips from different vendors, they're not going to sell those to you at the area plus some margin. They will be supply chain curves, right? So whatever I can get for this chiplet, I will get for that chiplet. So the innovation here is that the economics of making just this thing, right, is complicated, right? So by doing this POC, you're not really solving much of technical problem. You're really trying to solve these business problems. Are people willing to kind of like come together, collaborate, and create this thing? And if you think about it, as a third party who's maybe taking chiplets from different vendors and putting a solution together, if you think about the design flow and the kind of like the testing flow, a few things come to mind, and this is kind of my thinking. Everybody needs to supply some kind of engineering system level models that don't have to be cycle accurate, because that includes a lot of IP, but they should be at least transaction level. And there should be some kind of IBIS models, which are basically interface electrical models, and people should be sharing that. Now, I think if that is available, along with this chiplet, that would tremendously help these designers who are putting the whole system together. Also, as I mentioned, that mechanical solution is important in here. So we have to learn to provide some kind of thermal models and mechanical models to go with it. The other thing is industry has tried to do pretty fancy JTAG solutions around 3D ICs. I think what we need is very simple traditional JTAG, something like 11, 49, 1, and 6, along those lines. So we are not inventing anything new. We're just asking that when you design a chiplet, should put a JTAG interface that complies with that. It especially becomes important if you have AC coupled SerDes. So when you get this material in, then there is a question that comes, hey, I'm getting all these chiplets from this source and all these chiplets from this source. Should we test each and every chiplet before we put them together? If you start testing each and every chiplet, your costs are going to go up. So I think what you really have to deal with here is how do you do yield management? That's important. Maybe you can just add a step for visual inspection, or just go with the guarantees that are being put in place. And I think that framework is another important thing that goes into the novel business model, right? How do people kind of like guarantee this material movement? And obviously, if you're building substrates in silicon or in organics, you have to test them. Just use the standard e-test. And after you build this thing, you most likely will need X-ray inspections for all the things to be. But that kind of becomes like a visual thing, and companies have a lot of experience in doing that. The last thing, which is quite complicated, is system level testing. And every single solution you build, you have to develop a different system level test, which is essentially after packaging. And so there has to be some kind of thinking about this one as well if we want to standardize. But you can leave that up to the integrator. Quality and reliability, any of that problems, I don't think we need to standardize anything. It's just be the responsibility of the designer, the integrator, and fabs and whatnot. So you go to the next one. There's really one thing that changes in here, that you are adding the cost of that silicon interposer, but you're buying better power, you're buying better coefficient of thermal expansion match, which is another complexity of mechanical design going into substrate, especially for high performance things. So that's why you are seeing some companies are actually already shipping products like this. They're already in the market, right? But they are taking the hit for the silicon interposer cost, right? But at some point, it probably makes sense with additional value. That's actually another thing, all these gray rectangles, that is where all the innovation is, and that is what makes the technology kind of move forward. Green rectangles are just a retrofit, and we can just keep on using them as long as they make sense for certain applications. But I believe that kind of going in the direction of something of this nature is what solves the problem in the long term. zGlue wants to be there. That's the direction that we are trying to go. But it's not like a sudden transition between last slide and this slide. But if you think from cost point of view, if you can pull in, let's say, chip number 3 and chip number 4 functionality into the interposer, you have now flipped the whole cost of silicon integration in your favor. And if you do this calculation on a regular basis, you would figure out, okay, heterogeneous integration of this nature is the future, because we now don't have to worry about the additional dark silicon. But the other side effect is that engineering of this thing is super complicated, and that excites me as an engineer, because there are tons of other problems that I would keep on solving for next few decades, right? So, but I think what we should do in this group is try to enable people so they can easily exchange their chiplets and kind of like, pick from different sources without creating too much issue about intellectual property, yet be able to benefit and be able to kind of like share margins. I think that's kind of the future in a way. What happens with this type of solution, actually testing flow kind of stays the same, but the constraint on getting engineering levels, system level models from other parties is less of a issue, because you are pulling some of the functionality into the interposer. So that helps, and quite honestly, this is really what we have done at zGlue. What we have done is we've just put in a lot of testability into our fabric. Our fabric is agnostic to incoming footprints, electricals, protocols, and not only that, we put some programmability on top of it, which pushes a lot of functionality into software, but at the cost of additional area and some of the additional hit that you take. But we get pretty amazing turnaround time, right? So and what happens is, in our particular case, when a solution kind of tends in that direction, from cost point of view, sometimes it actually turns out to be better than printed circuit boards. People just laugh at me at some points, but when I show them calculation, it's like, oh, it kind of makes sense. If you don't have dark silicon, and especially if the interposer silicon is not in 40 nanometer or 7 nanometer, it's a lot cheaper, and its raw material is actually sand, not petroleum. So in the long run, it should be cheaper, right?
So, but in that case, we are putting other functionality into the interposer chip.
Right.
So, I mean, you cannot really build it at like 65 nanometer or something. I mean, the C3 and C4 are important, like fast IPs.
Yeah.
Then it has to be built.
Right. Those are great questions, and that's where, companies should think and they should innovate. They should figure out how they want to disintegrate and reintegrate this whole thing, right? It looks like that, say if you are making a CPU in 7 nanometer, it doesn't make sense to put that in the interposer. But if you are making, let's say, radios of some kind, right, that require larger geometries, it probably would make sense, things of that nature. So this thing opens up a bunch of other dimensions for designers to think about and to innovate on.
Good question. So in the ecosystem that we need to have for this to work, right? Are you saying that there'll have to be many variations of C3 plus C4 plus silicon interposer in the market so that they pick and choose, depending on who's going to make that?
So let's say I'm zGlue, I want to make C3 plus C4 plus silicon interposer, right? But I also want to get C1 and C3, sorry, wrong numbers there, but the other chiplets, right? I want to be able to get that information, be able to use that easily. But, maybe at some point we can standardize the interposers, just like the DARPA is trying to do. But then I really think that this should be left to the designers, companies like, companies that are in the business of making chips, that they should be the ones who should be focusing on putting the chip level solutions together. I'm not sure if there's an easy way to standardize it by saying, oh, this ball goes here and that ball goes there. It's just, we've kind of struggled with that quite a bit, and in the end realized there's a little bit of customization that you can do at top metal layers, but the moment you hit like transistors underneath, you don't really want to deal with that too much.
It's been made through silicon via.
Yes and no. We did it without through silicon vias. Our technology works without it. But yeah, sure, it will be awesome in this diagram, the way I put it together. So if you want high performance, you probably are better off using through silicon vias. With the moment you go into through silicon vias, then you have to pay even more attention to power dissipation, because you're thinning the substrate so much and heat just goes through it to the next level and kind of affects things there. So I'm not saying that, pick this technology or that technology. I'm just saying I think there should be a marketplace that people can interoperate and sell their chips and be able to build systems of this nature.
This level of further optimization, obviously, it could prove to be very cost effective. I think the question in my mind, and perhaps on others, is just that the scale that one can do that. One can see, relatively small devices where you include some functionality in the active silicon, but for large pieces of functionality that are, billions of gates, that obviously is a limitation. I'm not sure where the practical crossover is.
Right. And I just wanted to start a discussion, and you guys can figure out a solution, right? With smart people, right? There may be a solution between this slide and the previous slide, right? All what I'm saying is there's gold here, okay?
What's the biggest silicon interposer you've built?
Me as a company? Oh, we are focused on ultra low power devices where we can readily get chiplets from third parties. Our devices are really, really small. You are talking about, of the order of 10 millimeter on a side, and we have various cuts going down to 5 millimeter on the side. But the thing is, if you are building these IoT devices that have 100,000 units, one SKU, you're not going to make a chip for that, right? By the way, same applies to your automobile, right? Each car probably is going to sell a limited amount, so it doesn't make sense to do the whole SoC. It's better to just build these things in a Lego manner. That's why the whole DARPA program comes about for their airplanes and stuff, right? So few other things that I would like to mention about the POC 1 that we are talking about. So there are a few limitations here. I think it's the right baby step, but the chiplets have already been designed. There's really not much that you can do on the interfaces, so you just have to deal with it. And just like in the previous diagram, something like a BGA multi-chip module will make sense. And also, the testing of individual chiplets, even if we come up with a standard, there's no time to do that. I think for next POCs or next things, we should consider. But in the detailed electrical architecture of this POC, we should put some effort in to figure out how to use JTAG and be able to at least test the yield of every component individually, because that will help in the next rev. That, after you build, you at least want to debug and be able to assign that, this component isn't working or that's not working. For POC may not matter, but for the sake of developing kind of like a gentleman's agreement, probably will be a good thing. So I want to leave you with a few calls to action here based on my learning. And by the way, I'll be happy to answer any questions and while I talk about these things. So number one, we have to figure out a very simple testing methodology without inventing new protocols or new variants that are proprietary, because I believe JTAG provides you all of it. And we just need to think about what will be the method in this marketplace. How do we guarantee that chiplet is tested to the same standard as any other chip, right? So it has to go through sort, it has to go through post-packaging tests, all of that at the monetization point. Also, we should come up with a list of collaterals that the chiplet providers have to kind of commit to. Obviously, data sheets, engineering system level models, interface models, this is the minimum. And for high performance, it would be nice to have some kind of mechanical models and thermal models so people can build a system and do those simulations. Previous efforts that just went bottoms up, they suffered horribly because of lack of that and not paying attention to thermal issues, right? So now people have been burned and they kind of do it, but if you want to create a marketplace, let's just make sure that data gets exchanged. Also, as I mentioned, we have to think of these chiplets as really chips, right? So the contracts around them in terms of yield and cost should be identical. One big problem here is if one chip doesn't work, you lose all other bill of materials. So you need to test these chiplets to maybe a little better testing criteria. If you don't, you have to think about building built-in self-test and recovery mechanisms, which can compensate for some of these issues. And lastly, we need to come up, or the industry needs to come up with what's called process design kit. Silicon designers think of it as air and water, but packaged in the packaging world is just no two companies talk to each other and everybody has different way of thinking. So if we want the CAD tools to kind of coalesce around this particular effort, the assemblers and the manufacturers have to kind of like come up with some bare minimum standard way that CAD tools from one particular company.
Very good.
Right.
Great stuff. Enjoy it.